This is called the fundamental theorem of calculus. We're doing this mainly so that when we move on and look at integration using substitution and integration using parts and integration of partial fractions, which is the rest of the course after today, so that we're familiar with the notation and the algebra involved. What we have seen is that under a very specific set of circumstances, if one function lies entirely above another function, I don't even want to go there. Let's go back to the simplest case where you have a single function that lies entirely above the x-axis from a to b. We have seen that the area can be found by integrating the function using x as something that everything is with respect to, integrating the function from a to b, and what that means is you take the antiderivative at b minus the antiderivative at a. Okay? Where capital F prime will give you f of x. In other words, capital F is the antiderivative of f of x. But it doesn't have to represent an area. This statement, I know algebraically and mathematically it seems weird for me to just say, well, it's always true. Of course it's always true. It's just algebra. But it has meanings, even if it's not an area. And this idea, this statement, is actually called the fundamental theorem of calculus. It's that important to what you do in calculus. The precise meaning of the value that you get when you anti-differentiate the function and then put in the two numbers and subtract the results, the exact meaning depends on the situation. I'm going to go with a situation that some of you will be familiar with, but not all of you, and that's okay. It turns out that in physics, there is this quantity called impulse. And it has to do with how much an object's momentum changes by. You don't have to understand the deep meaning of the physics here. It has a physical meaning in the real world. If I tell you that a rocket experiences this much impulse, it tells you something about the rocket. If I tell you a passenger in an automobile collision experiences this much impulse, it tells you something about the collision the person experienced. And this is a pretty contrived graph, but what we're talking about here is an object being jostled back and forth by a force. For the first 4 seconds, there is a force that's in a negative direction. So the object is being forced south, maybe. Let's not worry about which direction the object's moving because that's not relevant. At the end of the 4 seconds, the force changes. Well, it's changing throughout the whole time, but it changes from being negative to positive, and that means during that time the object is forced in a positive direction. And for up until, what, 7.5 seconds it looks like, and then up from 7.5 seconds up to what looks to be 13 seconds, it's forced in a negative direction again. And if I told you that you had these 3 areas, by the way, this would mean the integral from 0 to 4 of the function would be negative 25. Because the area is 25, that's what that 25 is telling you, and it's below the x-axis, which means it's negative. This is telling you that the integral from 4 to 7.5 of the function is positive 16. And this part is telling you the integral from 7.5 to 13 of the function is equal to 62. Okay? And I did talk with you about this before. I gave you a similar example, but I want to go a little bit deeper with this now. That if I said to you from a purely mathematical standpoint in this question, if I said find the area between y equals 0 or f equals 0 from 0 to 13 seconds. You couldn't do this. That would not give you the area from a geometric standpoint. Because when you take a look at this, the area is, and you can check my arithmetic, 25 plus 16 plus 62. 103? Pretty sure it's 103. The area, if I said, what is the area, the physical area between them, you'd get 103. But we know, even if you haven't taken physics, since some of this force is in one direction and some of the force is in the other direction, there's kind of a canceling effect that happens here. And the impulse is not going to be 103. The impulse is going to be 62 plus 25 minus 16, and whatever you get, it will be in a negative direction. And even though these three individual integrals give you some information about area, this integral from 0 to 13 of f of t dt, without regard to what the graph looks like, just blindly doing the antiderivative or the integral, will give you negative 71, I believe. Can you double check my arithmetic there? I'm taking the areas that are below the x-axis and I'm assigning them negatives, and then I'm adding the 16. So this is how much impulse there is. This is the impulse. This is what truly happens. It has a meaning. And as I said before, if we want, you can divide that by the 13 seconds and get the average force. There's lots of applications to this. So I'm just giving you this to ponder because I started off by saying it doesn't matter what the number is. The precise meaning depends on the situation. And you're going to be doing some problems where you'll get an answer here and you'll get a negative and you will think you have done something wrong because it's supposed to be area. Not today. It's only area if you're working on area. So let's talk about properties of integrals, which is the most important aspect of today's lesson. When you see that, the integral of f of x dx, this is called an indefinite integral. And it's simply equal to the antiderivative of the function. I hope you understand that when I say this, I'm saying equal to the antiderivative of the function. And if you're like me, and I believe most calculus students, you go, well, obviously, I've already been taught that. There's a lot of what we're doing today that you already know. This is called a definite integral. So as soon as you take that integral and you start evaluating it over an interval, it is called a definite integral. And it's found by anti-differentiating the function and evaluating the antiderivative at b minus the antiderivative at a. So far, the only new thing is what we call these. This is called a definite integral. This is called an indefinite integral. You can kind of try to remember that because definite integral means it's definitely equal to something. You're putting a number in. I hope it goes without saying that an indefinite integral needs to have plus c attached to it. It's not an area. Two very important properties of integrals, and they're not going to seem that important today, but starting tomorrow and till the end of the semester, they will be crucial. The integral of a constant times a function is the same as the constant times the integral of the function. Let me give you a perfect illustration of how useful this idea is. I want to transport you back in time to when we first learned about antiderivatives. And I said to you, well, let's say f of x is negative 3/7 x to the 4. What is the antiderivative? Do you remember us fumbling around trying to find the coefficient of the antiderivative that would make it work? You don't have to do that. Because what I'm asking you to do, if I say, what is this? I'm asking you to determine this. Right? This property says a constant times a function as an integrand, you can instead take the constant times the antiderivative of the integrand. You can take that constant and write it outside the integral operation, which means this is negative 3/7 times the integral of x to the 4 dx. And this is x to the 5 over 5. You don't have to think at all about trying to make that correction to get the right coefficient. You understand what I'm referring to, right? I mean, we were fumbling around on that for a very long time. But this will simply be that. Because anti-differentiating x to the 4 is child's play. And then you can multiply those numbers. So by introducing this notation along with this rule, it just makes things so much easier. It's a simple idea, but it really changes the game. Number 4 is a property of integrals that we probably wouldn't ever use on a day-to-day basis, but we will need to use it later. You know what that's saying? If I tell you, going back in time, that you want to find the antiderivative of this, then what I'm telling you is I want you to find the antiderivative of that, right? This is the new notation. But then what I'm telling you is that means this. And I will be the first to admit that doesn't really help you any. We do that anyway. This is exactly like me telling you about that rule with derivatives. The derivative of a sum is the sum of the derivatives. So I want to walk away from this for a second. And this is, what I'm teaching you is all by design. It's not just trivial. It's important. If we go back to derivatives, if I say to you, what is the derivative with respect to x of x cubed plus x squared? We just write 3x squared plus 2x, don't we? Okay, but what this rule is saying is for derivatives, that's what you're allowed to do. The derivative of a sum is the sum of derivatives. Not so with product or quotient. That's all this rule says. That's all Rule 4 says, except it's in reference to antiderivatives. So, of course, this is 1/3 x cubed. And does anybody want to tell me what the antiderivative of cotangent of x is? Good luck. That's not really going to help you. Leading up to what we're going to talk about tomorrow, the natural logarithm of the sine of x, because the derivative of ln of sine is 1 over sine times the derivative of sine, which is cosine, which gives us cotangent. Tomorrow, I threw this in because tomorrow we'll look at a formal way of learning how to do that. And finally, the other point I want to make here is that properties 3 and 4 are also true for definite integrals. So when you look at a definite integral, that's where you're putting in numbers for a and b at the end. When you anti-differentiate, you're allowed to use all of the properties, even though you're going to evaluate it as a number. This here on the right-hand side of the screen maybe illustrates one of the most important points today, is we're getting more and more involved with this notation, which allows us to do things in a more streamlined fashion. And that's going to continue starting tomorrow. Like I said, from tomorrow to the end of the semester, it's all about algebra with integrals. So let's take a look at some examples now. find the general indefinite integral in each case. The language has changed. This is not a question that you don't know how to do. You know how to do this. You don't have to write this down. I'm going to just because. Even that, you know what? Even that. Whoops. Nobody's really asked me why we got to have that dx there. It's a complicated issue. Let's just put it there for now, okay? You will likely get a prof or an instructor that when you first learn the fundamental theorem of calculus, which is what we're doing here, they will write this. You can go right to the answer. I know you can go right to the answer. But to illustrate to you the properties of integrals, this becomes 6 times the integral of x cubed dx. This becomes plus -1 times the integral of secant squared of x dx. This becomes plus 3 times the integral of e to the 2x dx. And this becomes pi times the integral of 1 dx. I know you don't need to do that. Okay? And I hope you know that you don't need to do that. But, well, listen, even me, and I know that sounds braggartly, but I'm not saying it that way. But even me, when you say, what is the antiderivative of 6x cubed, I have to think a little bit longer and a little bit harder than saying, what's the antiderivative of x cubed? So by me just parking that 6 outside and then saying 1/4 x cubed, oh, it's 3/2 x cubed. Or 3/2 x to the 4, rather. And I would have got there eventually, but it's so much easier. Here, -1, I think tangent has a derivative of secant squared. I just want to make sure about that before I write it. So is the derivative of tangent secant squared? Yes. So this is minus tan of x. See, I know the antiderivative of e to the 2x is 1/2 e to the 2x, and that should be fairly easy for you. I need that half because of the chain rule. And I really want to see if I can make this point clearer. Going from here to here, to me, is easier than going from here to here. I know it shouldn't be that way. I know that. The logical part of my brain says, what difference does it make? But it is easier in yellow. And then, what is the antiderivative of dx? It's x, so plus pi x. And we can throw a c on there. And I'm not going to bother to rewrite this. You can write this as 3/2 for a coefficient of the first term. You can write it as 3/2 for a coefficient of the third term. But we're done. Any questions with that example? Okay, so what is the antiderivative here? Well, first of all, why don't we pull that 3 out? I love this question because there are so many different answers. And I'm not just talking about that constant c. Well, I kind of am. So, any takers? Maybe not on what it is, but what we can do to find out what it is.
Is it 1/2 sine
Yes? I'm not going to bother asking you to explain what went on in your head to figure that out. It probably just kind of is like a flash of intuition that, well, if I have sine squared, when I swing that 2 out in front, the base of sine x stays the same, and I lose 1 from the exponent, and then I have to multiply by the derivative of sine. So this is the thinking. Sine squared of x is this. And we're doing the differentiating what we think the answer is to see if it gives us what we were supposed to anti-differentiate test. So if I differentiate this, the 2 comes out in front, the base stays the same. I drop 1 from the exponent, and I write cos of x. Because the derivative of the argument of the power is the derivative of sine, which is cos. Any other takers? I mean, why couldn't we do this? Right, because I'm going to swing that 2 down. It'll cancel with the half. Then I will have cos x raised to the 1 and multiply by the derivative of cos x, which is negative sine x, and the negative goes away because I saw that coming and I put a negative there. I really love this example. The math involved in this is phenomenal. But what you could do instead, we want the negative here because when we differentiate cos, we'll get another negative, which changes that negative to a positive, which is what we want. Okay. Bottom line is, these functions are all the same functions, but they're separated by a vertical displacement. Right, so they just have different constants associated with them. But if you used either of them to find areas, the areas would be the same because the shapes are the same over identical intervals. All right. Take a look at number 2. This is boring work now. You have to anti-differentiate and put the numbers in it, but it's good practice. So what we need to do is evaluate x cubed. See, and over here, everybody, this is the best way for me to think about what the antiderivative of the square root of 3x is I do this. It just, to me, it streamlines my thought process a bit. The square root of 3x is the square root of 3 times the square root of x. I can take that root 3 and write it outside. I still have to think about what this is, but there's less thinking involved. I increase the exponent by 1 and multiply by the reciprocal of it so that when I swing that down, I get the right answer. So quite frankly, I don't care how you write this. I'm going to write it as 2 root 3, and it's minus 2 root 3 over 3 x to the 3 halves. It doesn't matter how you write it because we're about to put in numbers for x. Minus 10x from 4 to 16. So we end up with 16 cubed, yuck, minus 2 root 3 over 3 times 16 to the 3 halves, minus 10 times 16. That's the result of putting 16 into the antiderivative. Now we have to subtract the same thing, but putting 4 in. number crunching time. 16 cubed. (16 cubed) minus 10 times 16 is 3936. (16 to the 3 halves). Well, to the halves means square root. The square root of 16 is 4. 4 cubed is 64. Times the negative 2 is negative 128. I have a root 3 over 3. I'm going to double check that with my calculator. Ignoring the root 3, 16 raised to the 1.5 times that 2 divided by that 3 is 1/28. It's okay. Then we have to subtract. What do we have here? 4 cubed is 64. 64 minus 10 times 4 is 64 minus 40, which is 24. And what do we have here? I'm looking right now, everybody, at this. The square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. So it's 16 root 3 over 3. (3936) minus 24 is 3912. 36 minus 24 is 12. Negative 128 things minus negative 16 things is negative 112 things. And the things are root 3 over 3's. This is the answer. What is it? Who knows? Is it an area? Maybe. Maybe it's an amount of energy. Maybe it's an amount of money. Maybe it's how many mice there are. Maybe it's a pressure in a tank. An average pressure. Could be anything. One final example, and this is just keeping us on our toes. How are we going to anti-differentiate that? Do you know, Alex? No? You do now.
Could you switch all of them to being like s squared divided by s?
That's exactly what we need to do. Otherwise, well, there's another way to do it, but it would be way more work, and you don't know how to do it yet. This is the integral from 1 to 2 of s squared over s. I wanted to just write s here. Minus s to the half over s plus 3 over s. ds. So this is the integral from 1 to 2 of s minus s to the negative half plus 3 over s. There's no point in me writing that last term as 3s to the negative 1 because it's a natural logarithm that's going to be the antiderivative. It's not a power issue. Are we okay with those three terms? I just saw a couple of, yeah, okay. I just saw some gestures or body language that I thought maybe somebody had some questions. So it's s squared over 2, that's the antiderivative of s, minus 2/3 s, nope, minus 2 s to the half. You got to really think about that sometimes. I want to get an exponent of negative a half, so I differentiate by wrapping that half in front and dropping 1 from the exponent, and then plus 3 ln s, and this is from 1 to 2. So I put in 2 squared over 2, minus 2. I hope you allow me that luxury of just writing root 2 rather than 2 to the half, plus 3 ln 2, and we want to subtract 1 squared over 2 minus 2 root 1 plus 3 ln 1. So we have some numbers here. 2 squared over 2 is 2. Minus a half is 3 halves. Minus 2 is negative 3 halves. I think when you take this and subtract, minus a negative, my mistake. I'm going to have to do that again. So it is 2 plus 2, which is 4, minus a half, which gives us 7 halves for those. Can you confirm that? You can confirm it by figuring out what this is first, and then taking the 2 squared over 2 and subtracting whatever that is. But I think we get 7 halves. Good, thank you, Jay. So we get 7 halves. I have plus a 3 ln 2. I just wanted so bad to write ln of 8. Move that 3 up. And that's it, because ln of 1 is 0. Oh, minus 2 root 2. I think the biggest thing is just getting used to this integral notation and being able to move those constants out in front whenever it suits your needs. It just makes things so much easier. That's the lesson. Tomorrow we're going to get into techniques of integration. So on page 505, question 1 to 3, every second letter, you're just, you know how I feel about this. Get some practice with some of the questions.